Hello everyone. In previous sessions, we have discussed how to do mole balance for single reaction as well as multiple reaction, and we have used their uh, extent of reaction coordinate as defined in many textbooks. For single reaction, there will be one extent of reaction, and for multiple reaction, there will be multiple extent of reactions. But there is another way of doing mole balance for multiple reaction as well as single reaction, which will not include the extent of reaction. Now, that type of expression can be obtained by using the balance of moles of atoms in the reacting system. If we balance the moles of atoms in the reacting system, we will get an equation like this, and we will have n equations. We will have n equations for n atoms. Suppose if there in a reacting system there is n atoms, then there will be n equations, and this Nj is the final moles of jth species. I will show how to do this in the upcoming lecture, but this method is very useful if you have more than two reactions. For two reactions, extent of reaction or using zeta, it will be easy. But if you have multiple reactions, then writing equation of this form will be very much useful. It will be seen later that this method will be used in thermodynamics for minimizing energy and something else. I will show the working of these expressions in the upcoming video. I will be solving a few past previous year gate questions. This will help you to understand how to use the zeta or how to use this using mole atom balance. Okay, let's go to the question. This is our first question. Now, if you read this question, it says formaldehyde is produced by oxidation or methanol reactor. That is written. Uh, we will now, if you read the question says that the product gas leaving the reacting to methane all are there. 60 mole per second methane enters the reaction. So in question it is mentioned that flow rate of CH4 naught, and the naught will be described as the initial value 60 moles per second, and also the methane, final methane FCH4, which we will be using the notation for uh, final CH4 in the system as 26 mole per second, 26 mole per second. Also, if O2 is also given, if O2 means the outlet oxygen, the outlet oxygen is 2 mole per second, 2 mole per second. The O2 is 2 mole per second, and CO2 is also given. If CO2 is equals to 4 mole per second. Now, in question, it has asked the molar flow rate of oxygen entering the reactor. Now, the molar flow rate of oxygen entering, so our main aim is to find FO2 naught. This is the main aim we have to find. Now, I will be doing this example in two ways. So, in first way, I will be using the extent of reaction using zeta or reaction or coordinate. Now, using reaction coordinate, we have we will use this expression F CH4 is equals to if CH4 not. Now, for getting the change in as we have shown, As for multiple reaction, we have shown that in multiple reactions, the final moles will be n. I have already written. However, this delta I is the change in stoichiometric coefficient, stoichiometric coefficient for single reaction. For the ith reaction, so not single ith reaction, and for single reaction we have not sorry for a species I we have NiO plus summation of nu ij zeta j. We will use this expression. Now for using this expression, see the reaction. CH4 has stoichiometric coefficient of -1 and -1 in here -1 and here also -1 in the stoichiometric coefficient. So the this expression will become minus epsilon 1 minus epsilon 2. This is one equation. And FCO2, FCO2 which is given in the question, we will be writing the expression for this whatever given in the question. CO2, it is given that FCO2 not, and where in our reaction where is CO2, only here it is present. Only here CO2 is present. So and its stoichiometric coefficient is positive 1 and it is in the second reaction. So it will be FCO2 naught plus epsilon 2. Now this is the second equation. And another expression for FO2 which is given like this. FO2 is equals to FO2 naught minus. Now if you see the reaction, FO2 is present in the reactant side. It has stoichiometric coefficient of -1 and stoichiometric coefficient of -2. So -1 epsilon and -2 epsilon 2. Sorry, not epsilon, zeta. -1 zeta 1 -2 zeta 2. Now this is the expression. These are the three equations we got because these why I have written these expressions CH4CO2 and not there are other species also not H2O or HCHO because in the question the data is given for only these three. So these expression and this data will be enough to solve the question. In GATE there will be enough information to solve the question. So have not you do not have to think that question is insufficient or something like that. Now, how to we these two values we know CH4 and CO2, O2 all know. So we can solve these two equations. Now, if we solve these two equations, if we add these two equations, the zeta adding one and two, we eliminate zeta two. So if we add these two equations, FCH4 plus FCO2 equals to FCH4 naught plus FCO2 naught minus zeta 1. Now all the values are given. CH4 given, CO2 given, CH4 not given, CO2 not which is 0 which is not entering in the reactor. So from here we are getting CH4 is 26. This is 26. CO2 4 is equals to CH4 naught is 60 plus 0 minus zeta 1. We will be getting zeta 1 as 30 mole per second. 30 mole per second. Similarly, using equation 2, we will get zeta 2 is equals to FCO2 minus FCO2 naught. If CO2 is present 4 mole per second, so zeta 2 is 4 mole per second. Remember, the extent of reaction or reaction coordinate has unit moles or moles per second, whatever you are using in the system. So from this zeta 1, zeta 2, we can easily get the value of FO2 naught. FO2 is given as FO2 which is supplied in the system 2, FO2 naught is unknown, zeta 1 is 30, minus 2 into zeta 2 is 8. So from here we get we get FO2 naught as 40 moles per second. 40 moles per second. So this is our answer. Inlet in the system 40 moles per second. Now I will solve this problem using moles of atom balance. Mole of atom balance. I will get the same answer. Now for this, we have to balance the moles of atoms. This this questions for using that. Suppose we are balancing the moles of C atom because CH4, CO2, all those values are given. So balancing moles of C single C atom, it will be beneficial. So let me balance the mole C atom. Mole C balance. Now, if we balance the moles C, we have to see initially in the system, we will do initially how many moles of C atoms is present. If CH4 is entering in the system, let me write the reaction here for easy identification. CH4 plus O2 gives HCHO, HCHO plus H2 plus water and another CH4 plus 2O2, CH4 plus 2O2 gives CO2 plus 2H2O. CO2 plus 2H2O. Okay, so this is our reaction. So this is our reaction. Now, how many in our reaction the feed entering in the system, it has only CH4. CH4 and each single CH4 atom, in each single CH4 molecule, there is only one CH4. Only one carbon atom. So it is only multiplied by 1. Let me write it properly. 1 into CH4 naught equals to now in the product, which will be the coming out of the reaction. CH4 is again coming out, which is unknown. CH4. CH4, if this value is given, so it is coming out. CH4 plus in HCHO also there is one carbon atom. So FHCHO plus, and in CO2 also there is one carbon atom. FCO2. This is one equation. This is one equation. From here we will get CH4, CO2, CH4 not all given. So here we can easily get the FHCHO. This is the HCHO compound coming out of the system, which is given by if HCHO CH4 naught is given by sorry, CH4 naught is given by 60 moles per second. 60 minus CH4 coming out of the system is 26 minus CO2 coming out of the system is 4. So HCHO is 30 mole per second. So HCHO coming out of the system is, or the after reaction, 30 moles per second. But our main aim is to find if O2 not. This is our main aim. So from here we are not getting any information. So let us do balance of mole of oxygen balance because target is oxygen, mole of oxygen, single oxygen atom balance. Now in the field O2 not means oxygen atom oxygen uh, is supplied. Now for each single oxygen molecule there will be two atoms. So the initial system is FO2 naught 2 into FO2 naught because there is two atoms in single oxygen molecule and in outlet also oxygen is coming 2FO2 because here also for the single molecule there is one single for single molecule there is two oxygen atoms. Now where are other oxygen atoms are there? Oxygen atom is also present in HCHO and as well as in H2O. In HCHO there is only single oxygen atom as also in H2O there is only single oxygen atom. So we will write is FHCHO plus FH2O. Any other oxygen atom? Yeah, in CO2 also there is oxygen atom present. For single CO2 molecule, there are two oxygen atoms present plus 2 into FCO2. Now this is our oxygen balance, single moles of oxygen atom balance. Now here we have few values. Here the unknown is H2O because O2, no, here O2 not is also unknown, H2O is also unknown. Let me simplify this expression to 2FO2 not is equals to FO2 outlet is given. Outlet is oxygen coming out of the system is 2 moles per second. 2 into 2, 4. HCHO is 30. FH2O is unknown. That's 2 into CO2. 2 into CO2 coming out of the system is 4 moles per second. So 2 into 4, 8. Right? 8. So this is our another expression where H2O and O2 is unknown. Now let me write another atom present in the system, moles of hydrogen atom because H2O is unknown, H is there. So let me balance moles of hydrogen atom. Now for writing moles H2 H atom, we see the reaction. CH4 is entering in the system. So see, for each single CH4 molecule, there will be four atom hydrogen present. So the expression will be 4FCH4 naught is which is equals to now in the uh, after reaction hydrogen atom is present in CH4 is present because CH4 is also coming out of the system. So we will write 4 into FCH4 plus HCHO has two atoms in single molecule, 2FHCHO plus in water there is also again two atoms in single molecule of water, two atoms, 2 into FH2O and any other? No, there is no other species that has hydrogen atom. So this is our expression. Now few values are already given. CH, we can anyway this equation will be divided by 2 because there is a common factor of 2. So we will divide by 2 and the values which are given as 2 into FCH4 naught is given by 660 is equals to 4, sorry, sorry. This is 2 into CH4 coming out of the system is CH4 coming out of the system is 26, 20, 2 into 26 moles per second plus 2 into HCHO is 30 plus, sorry, 2 will be not there because we have already divided by 2 plus FH2O. So this is the expression. From here we solve FH2 as 2 FH2 as 2 into 60 minus 26 is 60 minus 26 is 34 minus 30. We will get 2 2 into 34 minus 30 is 38. 38 moles per second. H2 is 38 moles per second. Now, from from this equation, moles of O2 balance, if H2O is known, we can easily calculate if O2 not. If O2 not is equals to 2 plus 15 plus 38 divided by 2 is 19 plus 4. So if we calculate, we get 40 moles per second. So from this method also, we are getting the same expression. So this method is very much useful. Same expression we got, 40 moles per second, but this method is more tedious. Like you have to write atom balance for each species. This will be helpful if there are multiple reactions, but for single or two reactions, writing each balance for each atom, it may be difficult. So this is one way of doing. These are the two ways of doing by using extent of reaction, which is done very quickly, and by using moles of atom balance. So we will be proceeding on the next question. So this is another question. This is GATE 2011 question. Now this question says that this following combustion reactions occur when methane is burnt, and 20% excess oxygen is supplied to the combustion. The conversion of methane is 80%, and the molar ratio of CO2 in the flue gas, which is the outlet, is 1 is to 3. Assuming the air has this composition, the O2 consumed as a percentage of oxygen entering the combustion. So percentage of O2 entering in the combustion. So we will write down first whatever given, and suppose this is the extent of reaction zeta 1 and This is the extent of reaction zeta 2 for first and second reaction. 20% excess air is supplied. So this means the conversion XCH4, which is given in the co- question, X conversion in it is in the question, which is 80%, 80%, which is 0.8. Also, if CO to CO2 flow in the flue gas, if CO divided by FCO2, which is equals to 1 is to 3. Also, assuming the Fn2, the nitrogen in the feed of the system, it has 0.8% F air. I am writing all the things which are given in the question. It is very useful to write the data in your expression format, which is given in the question. Now our aim is to find the percentage of oxygen entering in the combustor, which is percentage of oxygen if O2 not is the entering the system, and suppose if O2 is the leaving the system, and percentage will be if O2 not. So we have to find this value. This is the percentage. Like if O2 not is the entering the system, and if O2 not minus if O2 is is consumed in the system. So it is kind of asking fractional conversion of oxygen. Fractional conversion of oxygen. So to find this, we will again write expression for for the things which are given. FCH4 is equals to FCH4 not. Now if you see the reaction, CH4 has stoichiometric coefficient of -1 and -2. So same as like this, minus zeta 1 minus 2 zeta 2, and it is also said that the conversion is zero point 0.8. So I will write this expression as zeta 1 plus 2 zeta 2 is equals to FCH4 not minus FCH4, which is equals to FCH4 not minus FCH4 not to 1 minus XCH4. Conversion is given as zero point 0.8, so this expression will come as 0.8 FCH4 naught. So this is one equation. This is one equation. Now in the flue gas, it is also given FCO by CO2. If FCO by FCO2. FCO is FCO naught, and then CO is 2 on 2 CO only in the second system, only in the second reactions. 2 zeta 2 divided by FCO2 naught. CO2 is in the first reaction, which is single one, stoichiometric coefficient is 1, zeta 1. Now if CO naught and CO2 naught both are 0, so 2 zeta 2 by zeta 1, this ratio is given as 1 to 3. So I will write it simply as zeta 1 is equals to 6 zeta 2. Now I can put the zeta 1 value here to get the entire reaction in entire algebraic expression in only one variable. 6 zeta 2. So I'm getting 6, 7. So I get 8 zeta 2 is equals to 0.8 FCH4 naught, which is equals to FCH4 naught is equals to 10 zeta 2. This is another expression. This is single expression. It has only one variable unknown. Now suppose suppose now we will do for oxygen, right? For oxygen, FO2 is equals to FO2 naught. Now oxygen where is present? Oxygen is present in the field 2 is 2 zeta 1 and 3 zeta 2, which is negative charge. So minus so minus 2 zeta 1 minus 3 zeta 2, which is equals to FO2 naught minus zeta 1. I will put as zeta 1, zeta 1, zeta 1. I will write zeta 1. Zeta 1 is 6, 6 zeta 2. So zeta 1 can be written as zeta 1 can be written as 6 zeta 2, 6 into 1 by 10 FCH4 naught, 0.6 FCH4 naught. So 2, so I will simplify the expression 1.2 plus 3 zeta 2. Zeta 2, 3 zeta 2, zeta 2 is also 3 by 10 FCH4 naught. I am writing everything in terms of CH4 naught, which is supplied in the feed. So this is 0.3 and FCH4 naught. CH4 naught. You have to do these calculations very quick actually for solving gate. I am explaining here, but you can do all these steps very quickly to do these things within the time limit. This is equals to FO2 naught minus 1.5 FCH4 naught. So I got FO2 naught minus FO2 is equals to 1.5 FCH4 naught. Now the theoretical value. Now the for theoretical value of the reaction for complete combustion of the system. See, CO is side reaction. For if you give enough oxygen, the entire methane will be converted to CO2. There will be no CO. So for complete combustion, theoretical oxygen supplied FO2TH, which is theoretical oxygen supplied, divided by the CH4 supplied in the system. This should be in the ratio of 2 is to 1 because O2 2 and 1 C. This will completely react without having in excess quantities, give CO2 and H2O. So theoretical oxygen supplied if O2 theoretical O2 theoretical naught is equals to twice FCH4 naught. Okay, so I will use this expression if O2 theoretical is equals to twice FCH4 naught. Now in the question it has said something like 20% excess is supplied. 20%, yeah, uh, uh, 20% excess air is supplied. So for 20% excess supplied, the O2 supplied means if O2 naught will be 1.2 times of if O2 theoretical, O2 not theoretical, which is equals to 1.2 times 2 FCH4 naught, which is equals to 2.4 FCH4 naught. So we get FO2 naught. So to compute this expression, we have we have to compute this expression. So getting for now, we got everything for computing that expression. If O2 naught minus F O2 divided by F O2 naught is equals to, now F O2 naught minus F O2 we got as this. This is the F O2 minus F O2 naught. Sorry, F O2 naught minus F O2, which is equals to 1.5 FCH4 naught divided by F O2 naught supplied is 2.4 FCH4 naught, which is equals to 1.5 by 2.4, and this is equals to 1.5 by 1.5 divided by 2.4, which is equals to 0.625. So the answer is 62.5%. So the option answer for this is the option B. So this is the option. So this is how you should do the mole balance. We can also do this using the mole atom balance, but it will get lengthier because you have to do atom balance for each each atom present in the reaction system. For two reactions, extent of reactions using extent of reactions will be very much easy.